We begin with a formal definition of a basis, along with an example of a basis itself. Hello, welcome to the Denali Academy. Today I'd like to talk a little bit about the notion of a basis of a vector space. And I'd like to go through a couple very simple linear algebra examples to give you a feel for what it is, and then talk about how it can be applied to quantitative investing. So let's start with a very simple set S that is composed of two vector elements, the vector 1, 1 and the vector 1, 0. Now these are both elements of R2, two vectors with two elements, and to be a basis for a space, the set that you claim as a basis needs to satisfy two properties. The first is the notion of linear independence. And what this is a minimal type property, I like to think of it as. What it says is that there is no redundancy in your basis elements. A formal definition is that any linear combination or weighted average of these two elements, which could be written this way for real numbers a1 and a2, if you had this equal to the 0 vector, the only way to do this would be if your constants or coefficients on these basis elements were both 0. And if we think about this equation, the bottom equation says a1 is 0, and the top one says a1 plus a2 is 0, and so substituting the first solution into the top, we see that they both have to be 0 for this to be true, and that shows that this is a linearly independent set. And you can imagine if there were n of these basis elements, and if you had this equation for non-zero a's, what it would say by rearranging is that one of the elements could be written as a linear combination of the rest, and would therefore be redundant because you could describe him by the other ones. So this is a minimal property that you don't have redundancies built into your set. The second thing that you need to satisfy to be a basis is the notion of spanning. And this is a neat idea. The span of the set S is simply all of these possible linear combinations for any a1 and a2 real numbers. That is called the span, all the vectors you pick up. And I like to think of this as a maximal type property because it says you have enough basis elements to pick everyone up in the space. So for example, if I had the vector b, 1, 2, I could write this as 2 of the first guys, first basis element, plus a negative 1 times the second. And that would give me b. So that shows that B is in the span of this set. And this set does in fact span R2. One way to show that is by writing the elements column-wise as a matrix and computing the determinant of this matrix. In this case, the determinant is not 0. And that means that this matrix is invertible, and so you can pick everyone up with linear combinations. Now, the notion of a basis is much more general, in fact, than just these vectors. And that's done through this coordinate or coefficients. So if we think of what we did here with B, we represented B relative to the basis S. And the way we did that, one can think of as using these coefficients, 2, negative 1. These are, in fact, the coordinates of B relative to this basis. Now there are other bases for R2, and it's in general not unique. What is unique is the dimension, or the number of basis elements. So B relative to S can be represented by this vector 2, -1. And so your space can be quite general. You could have functions or different types of things in your space. And through this coordinate map, you can talk about representing elements of your space via vectors in a general setting, or Rn. And that allows you to use all these linear algebra tools to talk about very general vector spaces. So that's nice. So this is a simple two-dimensional basis. And the key points are to remember you have to satisfy two things: linearly independent spanning set.